Okay, so welcome back to the course of Introduction to Algorithms. In this lesson, we will talk about greedy. So what is a greedy? Greedy algorithm is algorithmic strategy or maybe technique or approach that makes the best optimal choice at each small stage. And in the end, greedy hopes that it will find the global optimal solution. Um, At each step, Greedy tries to find localized optimal solution, but it's not always leads to the global optimal solution. Of course, in most of the cases, it may lead, but it's not always guaranteed that it will find the global optimal solution. Um, so, as example, let's take a look in this problem where we need to choose the greedy approach. So let's say that we have 5 jobs to do, right? And each job has its own deadline, like 2, 1, 3, 2, and 1. And each job has profit as a sequence. So our goal is to get the maximum profit. So what do we do? Um, First of all, as you can see here, we have 3 deadlines, like 3 unique deadlines. It is a 1, here 2, and 3. So for each time slot, we need to choose the job with the maximum profit. So first of all, for the time slot 1, what do? We go through each job. Here we have the first candidate and it has a profit of 100. Then this job has deadline 3, then this job has deadline 2, and this deadline has a job of 1. So, but it has the profit of 20, so we choose the maximum job with the maximum profit and fill up its with we choose job 2. Then for the time slot number 2, we need to again go through the jobs. So again we have the first candidate with a profit of 60, then second candidate with a profit of 40. So we choose the job J1. It has a profit of 60. Okay. Then for the job number 3, we have the only candidate. We don't have any choices here. So we choose the job 3 with a profit of 20. So in the end, we have 3 jobs, like 100 for the time slot number 1. For the time slot number 2, we have 60. And for the time slot number 3, we have only one choice, which is job here 3 with a profit 20. Okay, so if we sum up all the jobs, the result is equal to the 180, right? And this is a global optimal solution. We cannot get even more, even higher profit. So here, for the job number 1, we choose the local optimal solution, which was J2 with a profit 100. For the 2, we choose another local optimal solution with profit of 60. And for the third one, we have only one choice, which is a job 3. And as you can see, we cannot get even higher profit. So this is a global optimal solution. So our greedy approach helped us to find the global optimal solution. So the result is this one. What is the time complexity? The time complexity, because for each slot we choose, we need to go through all jobs. And if we have 3 jobs, at most cases, our time complexity would be big of n squared. Can we do better? Yeah, we can do better. We can sort all the jobs according to its deadline. and it would help us to not to go every time through the whole jobs and to choose the global optimal solution each step. Can we do better? Yeah, of course we can sort again sort the jobs according to deadline and profit. In that case, the time complexity is going to be big O of n log n. So next problem, we have infinite number of coins with this kind of denominations. So 1, 5, 10, and 20. And we need to change 38. And we need to use minimum number of coins to change 38. So we need to apply the greedy approach. And if we apply the greedy approach, in this problem we need to choose the coin with the maximum value, which is a 20. So first we take 20, right? Then again we have 10 as a choice. We take 10. We cannot take the second time 20 because in that case the sum will be equal to the 40. That's why we need to choose 10. So this is the second step. On the third step, so right now we have 20 and the 10. So we right now have total 30, and we need to change also 8. So here we cannot choose 20 because if it is 20, it's in the total it's gonna be 50. We cannot choose 10 because in that case the total gonna be 40. Here we have two choices, so we choose a coin with the maximum value, which is a 5. In that case, the value gonna be 35, right? Then on next step, we need to change 3, and we choose 1 3 times, and in that case, our total number of coins will be equal to 38, and we would use 6 coins. Is it a global optimal solution? Yes, it's a global optimal solution because we cannot find any other way to use even less number of coins to change 38. So our solution, our greedy approach helped us to find the global optimal solution, which is equal to 38. So, but there can be other situation when the greedy approach doesn't lead to the global optimal solution. So let's say that we have this number of coins, infinite number of coins with these denominations 1, 15, and 25, and we need to change 30. So again, let's use same approach as we used here, like choose coins with the highest value at each step. So first we take 25, right? So from the 30 we subtract 25 and we have 5. Then we cannot choose 15 because 15 is bigger than the 5, and we need to choose 5. We need to choose 1, and we need to do it 5 times. So in that case we will get 25 and 1 1 1 1 1, and in that case we would use 6 coins. But this 6 coins is not our global optimal solution. Actually, the global optimal solution is 2 coins, because if we would use 2 times 15, it would be like only 2 coins, and it would change 30. So as you can see, in the previous example, in this example, greedy approach worked to find the global optimal solution, But in this example, it didn't work. So so as you can see, the greedy solution doesn't always find the global optimal solution. So um, why greedy doesn't always find the global optimal solution? Let's say that you are staying here, and your goal is to find the highest mountain. And initially you don't know where is the highest mountain, and you're staying here between these two mountains. And when you are staying here, you see only two mountains: this mountain and this mountain. And in order to find the highest mountain, you have the two choices, like go to this mountain or go to this mountain. And you may think that if you go to the highest mountain, to higher mountain, it can lead to the highest mountain. So it's like you're choosing local optimal solution, and you're going up here. But the global optimal solution would be located here. This is it. And when you go up to that mountain, you see that the highest mountain is located here, and actually you needed to go in this direction. So that's why like greedy doesn't always guarantees us global optimal solution. And the next problem, it's called interval scheduling. So let's say that we have some set of requests, and each request has a starting time and finish time. And let's say that we have one room, and we have the many requests to have the meeting in that room. And our goal is to satisfy as many requests as possible to find the largest compatible subset of the requests. So in order to, how can we apply the greedy to this problem? In order to apply the greedy algorithm, we need to choose the parameter by which we need to choose local optimal solution. So one of the biggest challenges in a problem when you want to use greedy is to choose the right characteristic for the problem by which you will identify local optimal solution. For example, uh, we can choose the earliest start time. If we choose earliest start time, we could have this kind of situation. Let's say that we have this kind of requests. This is the starting time. This is the finish time. This is the starting time and finish time until the end of all the requests. So let's say that we have this kind of requests, and this is the time. And let's say that we choose the request with the earliest start time, and let's say that we choose this one. In that case, we need to decline this request. Because we choose this one, because we cannot have two or more meetings in a room, and because we choose the request with the early start time, this one, we had to decline all other requests. But here the optimal solution would be to choose this meeting, then this meeting, then this meeting, then this meeting, and this meeting, and in that case we would satisfy 5 requests. Okay, we can choose the smallest request first, like request which has the smallest duration. So, but in that case, we could have this situation like this one. We have 3 requests. The request one has this starting time and this finish time, this starting time and this finish time, this starting time and this finish time. And if we would choose the meeting with the smallest request, we could have this. We could choose this request and decline this request. But the optimal solution would be to we can choose the smallest number of overlaps, but we could have this situation. Let's say that we have this kind of requests, as you can see, and if we choose the request with the smallest number of overlaps, like this one, we had to, because we choose this request, we have to decline this request and this request. And in that case, it wouldn't be our optimal solution. Here, the optimal solution would be equal to the 4. Right? We need to choose this request, this request, this request, and this request. We can choose the earliest finish time. Yes, this approach would work in our greedy approach. So here, what do we do in our solution? Let's say that R is our complete set of requests, and A is a request that we accepted. So we launch some while loop, and this while loop will run while R is not empty. Choose the request that has the smallest finish time, add that request to I, and delete all the requests that overlap with this request and while. So let's say that we have this kind of requests, and this is the time. So first we choose this request, and because this request has the earliest finish time, because of that we need to decline this request and this request. Then we have this kind of requests to choose, and we choose the request with the earliest finish time, which is this one. And because we choose this one, we need to decline this request and this request. Then we have this request to choose. Because of this, here we choose the request with the earliest finish time, which is this one. And because of this, we need to cancel this, decline this one and this one. And in the end, we choose this request. So in the end, we would satisfy 4 requests, which is our global optimal solution. So what would be the time complexity of the solution? First of all, we need to sort requests in order of finish time, and it takes big O of n log n time complexity. And we would choose requests in order of increasing time, and it would take big O of n. And the overall time complexity would be big O of n log n. Next problem, it's called fractional knapsack. So let's say that we have some knapsack with a weight capacity of W, and we have some items with some kind of weight and value. And our goal is to fill up the knapsack to its capacity such that we maximize the value of items that we take. So let's say that we have the knapsack weight capacity equal to the 10, and we have 5 items. Each of the item has this kind of values and this kind of weight. So as I said before, one of the most challenging thing in the greedy is to choose the parameter by which we choose the items. So here press a pause, think about a couple minutes, and think which parameter do we need to choose to apply as a greedy approach. So in order to apply the greedy approach, we can get the proportion of the values to the weight. In that case, the item number 1 would have this kind of value. Item 2 would have 2, item 3 3, item 4 2, and item 5 4. So we just divided the values to its weight, and according to these values, we choose the items. So first of all, the highest value has item number 5, and in that case the value would be equal to the 8. Then we would choose item number 3, and it would have the value of 15. But also we need to take a look on the weights. So we have weight 2, and again it shouldn't exceed 10. 2 plus 5. Okay, then here it's equal to the 7. Then the third item, the third value would be 2.5, right? But the item number 1 has weight of 4. In that case, it would be more than the if we take whole item, the value that we take would be equal to the 11, which is more than this. So we take only like 75% of this item, and in that case, like we would take the 75% of the item. In that case, the weight will be 5 plus 3 of this weight, and it's equal to the 10. And in the total, total value would be equal to 30.5. Greedy, first of all, is the approach, it's a technique to find the solutions. And there are many algorithms that use greedy to solve some of the problems. And one of them is the Huffman coding. So what is a Huffman coding? Huffman coding is the algorithm for doing data compression, and it forms the basic idea behind the file compression. It was developed by David Huffman while he was a student at Massachusetts at MIT. And initially, this algorithm was published in a paper of method for the construction of minimum redundancy calls. So let's say that initially we had some sentence, very long sentence, and we calculated the frequency of each character, and as a result we got these values. So A repeats 10 times, E repeats 15, I repeats 12, O this value, U4, S 13, T 1. So what does the Huffman coding do? We sort the characters according to its frequency, from the smallest frequency to the biggest frequency, and on each step we take the two values with the smallest frequency. It's a T and O. We adapt them, and we build this kind of tree. Then on the next step we again choose another two smallest values, which is this one and this one, and we build the binary tree from that, and as a root we calculate the sum of these two values, like this one, and we got this situation. Then on the next step we again take the smallest frequency numbers, which is 8 and 10, and we build like binary tree from them, and as a root we get the sum of these two values. So it's 10, it's 18, and we got this binary tree. Then on the next step we again take the values with the smallest numbers, which is 12 and 13, and we again build another tree. so we got 25. Like here we got the 25 as a root of this tree. So we would have two trees. One tree is this one, and second tree is this one. Then we would again take the smallest numbers, which is 18 and 15, and we would connect them, and we would have this kind of tree, like 33. The root would be 33. Then in the end we would have two separate trees, and we just would connect them, and we would have this kind of binary tree. Actually, it's called Huffman tree. This is not end of the algorithm. On the next step, we start from the root of the tree, and for the left side we give 0. For the right edge we give 1, and it repeats on each level of the tree. So here we do that till the end of the tree, right? So here it's this edge 0, this edge 1, and we do that till the end of the tree. And from that we start to build the coding. So for example, I would be the collection of the paths from the root to the I. So it's 0 and 0. So here, as you can see, it's 0 and 0. For example, E would be 0, so this path and this path. It would be 0, and it would be 1 and 0. So as you can see, 1 and 0. Then, for example, for the U, it would be 1, 1, 0, and 1. So it would be 1, 1, 0, and 1. So for the U, it's 1, 1, 0, 1. And that happens for each letter. So here, as you can see, this algorithm is very efficient. Like, it's a data compression algorithm, which means that it makes information much shorter. Because, for example, here, as you can see, even though that E, for example, here repeats 15 times, E gets very small coding. Just consists of the 2 digits, while the letters with the less frequency gets longer data compression. For example, T just repeats once, but it has this like compression consists of the 5 digits. So it helps us to like use less digits for the letters that repeats many more times. Next algorithm that uses the greedy approach is the Dijkstra algorithm. So what is the Dijkstra? Dijkstra algorithm is an algorithm that finds the shortest path between nodes in a weighted graph. It was created by Edgar Wipe Dijkstra in 1972. He got the Turing Award for this algorithm, and the Turing Award is a kind of Nobel Prize in computer science. So how does the Dijkstra algorithm work? Let's say that we have this kind of weighted directed graph, and let's say that we have some starting point with this node S, and the Dijkstra algorithm finds the shortest path to each node. So initially we have 2 edges that goes from the S. It's one edge goes to the T, and one edge goes to the Y. And we take the edge with the shortest, like with the smallest weight, which is the edge that goes from S to Y. So here, initially, as you can see, the values like shortest path from the S, initially all of them the infinity, because we don't know yet the shortest path to these nodes. And here we start from the S, and one edge goes to the Y, second edge goes to the T. And initially we say that T, the shortest path from the S to the T is equal to the 10, and the shortest path from the S to the Y equal to the 5. And we take the path that has the smallest weight, which is the Y. Then when we go to the Y, we have the next choices. One edge that goes to the T, which is 3. Another edge that goes from the Y to the X has weight of the 9. And another edge that goes from the Y to the Z is 2. And so on the next step we say that the shortest path from the S to the X is the sum of the 5 plus 9 is equal to the 13. And the shortest path from the S to the Z it's 5 plus 2 equal to the 7. And here we update the result of the T, because T was initially 10, but here we found the even shorter path that goes from the Y, so 5 plus 3 is equal to the 8, so we update this result. Then from all these edges we take the path which has the smallest weight, which is goes to the Z. From Z we have two choices to go. It's one edge goes to the X with a weight of 6, and another edge that goes to the S with a weight of 7. So here we have another choice that goes from the T to the X with 1, and we choose the edge which has which has the smallest weight, which is the T from the edge that goes from the T to the X. And here we update the results, which is equal to the 14. So so it's equal to the 14. So we choose this one 6, and in the end it gets equal to the 14. Then on the next step we have the next choices. From the X we have the 4, one edge that goes to the Z, but in total it would be equal to the 11. It would be equal to the 18, but this value is smaller, and we could go to the T or to the X, and we choose the path that goes to the T. And from the T we have edges that goes to the Y and to the X, and we choose the edge with the smallest value, which is this one, and here we have 14, but this one, if we go from the T, the total weight would be equal to the 9. So in the end the result would be like this. But the X algorithm has one disadvantage, is that it doesn't work with the negative weighted wedges, because intuitively the X algorithm assumes that the path will always increase, and but when you have the graph with the negative edges, the shortest path can be in the end the path that can be the longest one. So but when we have the negative weighted edges, Bellman Ford we have another algorithm that considers all the possible ways, and there is algorithm called Bellman Ford which finds the shortest path with negative edges. So Bellman Fort uses dynamic programming approach. Meanwhile, Dijkstra uses greedy approach. Um, and as you can see here, the time complexity of the Dijkstra algorithm is E multiplied by log V. So E is the number of edges, V is the number of vertices, um, and the time complexity of Bellman Fort would be E multiplied by V. So as you can see, this has longer time, but it considers all the possible ways. Meanwhile, the Dijkstra algorithm takes less time, but the disadvantage of the Dijkstra algorithm is that it doesn't work on graphs with the negative weighted edges. And by the way, on following weeks, we will start to learn the dynamic programming and as well as Bellman Fort algorithm. So stay tuned on algorithms. So for this lecture, it's readings 2 chapters. It's from the book of the CLRS. It's chapter 16, and another chapter is 24.3. So that's it. Thank you very much. Thank you for your attention. See you next time. Bye.